I'd like to thank the conference organizers for inviting me to give this talk. This paper appears in the journal Computational Linguistics. Today I'm going to briefly distill the key points of the paper, which will provide some new views for analyzing and deploying existing networks and for analyzing their training data sets. We're going to cover a lot of ground in 12 minutes, and conceptually it's rather different than how we typically view neural networks. So before we dive into the details, let's briefly zoom out and get a high-level overview of the approach. In the context of document-level classification, for which we have document-level labels for training, we'll compose the input consisting of n tokens through a deep network as has become standard. Today, assume the deep network is the pre-trained transformer BERT. Now, core to the approach is that we can place a CNN over the hidden representations of the network, and from this we'll drive a very lightweight attention-style mechanism that turns out to have an inductive bias that is particularly conducive to backing out token-level labels. More specifically, the prediction task will be to predict the token-level labels, but we won't have token-level labels during training. This task, which is called zero-shot sequence labeling, turns out to be a surprisingly challenging endeavor, and since it corresponds to class-conditional feature detection, making progress on that task will take us into the heart of addressing the central concerns of neural network interpretability more generally. The CNN will also serve as a memory layer insofar as it produces dense representations that we'll use for matching. Now, once we have the token level predictions and representations, we'll match those against those associated with known labels. We'll refer to the set of representations with known labels as the support set. This will often be composed of data from the original training set, but as we'll see, in some cases we'll be able to update it with additional representations or by modifying the existing labels. Next, as a final step, we'll construct a canon approximation of the original model that is at least as strong as the original model and will give us an explicit connection to the support set useful for analyzing the model and the data, and this will also yield heuristics for prediction reliability and constraining the output. So in summary, at a high level, mechanically we're going to decompose the model first across the input down to a resolution lower than that for which we had annotated labels. Next, we're going to decompose each of those predictions as a weighted vote over the training set. A running example today will be for grammatical error detection. Additional tasks are provided in the paper. With this example, I'll go into further details of the two decompositions, and throughout I'll be highlighting the new properties that this approach adds. Just so that we're all clear on this front, in the zero-shot binary sequence labeling task, we're given document-level labels for training, but then at inference we're going to predict the token-level labels. Now, as a point of contrast, if we replace the document-level labels y uppercase with the token-level labels y lowercase, we'll arrive at supervised binary sequence labeling. Today we'll be considering the specific task of zero-shot grammatical error detection. We seek to label tokens with grammar errors with a positive class. This amounts to feature detection for the sentence-level classifier with the advantage that we'll have a well-specified ground truth for evaluation. There are two broad, seemingly intractable challenges when approaching this problem that motivate our approach. The first is that multiple annotation schemes could be consistent with the document-level labels. We'll need to think carefully about the inductive biases of both the architecture and the losses for each data set, and ideally has some flexibility in the approach to be adaptable to various priors we may have. Secondly, the parameters of the deep network are not identifiable, so the approaches we might use for low-parameter linear models are out. It won't be possible to directly resolve that issue, but with matching of the dense representations, we'll nonetheless gain some new levers for analyzing the data, the model, and constraining the predictions, and that may well be sufficient for some real-world applications. Let's take another quick look at this set of operations. This is still at a high level, but we'll need a few more details to really understand the results relative to soft detention mechanisms. We convolve a kernel with one CNN over the final layers of the deep network. If the input were just word embeddings, this would just amount to a relatively weak bag of words model. But in our case, the heavy lifting is going to be done by the transformer, and the CNN will simply serve to summarize those representations as a final bottleneck over the frozen lower layers. We then take a ReLU and a max pool and then compose that with a linear layer to get our document level prediction. So, setting aside the kernel with 1 and the input being the deep network, that should be familiar. But now the question is how exactly to get the token level predictions. It turns out that deterministically unfolding the forward paths I just described is exactly what we need. For each token that survived the max pooling, we'll combine the corresponding output of the filter map with the weights and biases of the linear layer. Note that m, the number of filters, is a hard constraint on the number of token level predictions. If m were 2, at max 2 tokens could receive positive token level predictions. For training, we have some flexibility depending on the resolution of the available labels and/or priors we may have about the distribution. Without placing additional constraints on the output, we can just train the final layer CNN with the standard cross-entropy loss against the document level labels, backing out the token level predictions as I just described. Alternatively, we can apply constraints to encourage sparsity. Reflecting the non-identifiability, the document level predictions may remain similar, which is why we'll typically also want some type of connection to the underlying training data to verify the patterns we see. Finally, at the other end of the spectrum, we can directly train at the lowest resolution of interest. Looking at the results on the test set, we see that it's a surprisingly difficult task to label at the token level rather than just aggregating features. An approach such as LIME, when used with a transformer, is only marginally better than a random baseline. Further, soft attention over LCMs or transformers is an improvement, but actually still only modestly better than a majority class baseline. For our approach, first let's consider a purposely limited capacity version with only 2 filters, which can only label at max 2 tokens per sentence. Already we see a big jump in the F0.5 score because we've gotten around the problem with the soft attention mechanism yielding diffuse predictions over the input. Key to the approach is that we can then increase the capacity here to 1000 filters without causing a blow up in the recall as with soft attention. These differences are substantive in practice when looking at the data. Importantly, we'll also then have a dense representation with which we can form a mapping to the training set. We see here that models with similar sentence level classification results can have significantly different token level results, so such mappings are critical. In order to make our connection to the training data, let's note that we can view each token level prediction f of x as the composition of u and v. The mapping v takes as input the word embeddings and hidden layers of the deep network corresponding to the particular token and produces a dense representation, a distilled summarization of the expressive deep network at the local level, which we refer to as an exemplar representation. The mapping U is then the max pool, ReLU, and the corresponding weights of the final fully connected layer that produce the token level prediction. We're going to collect all the exemplar representations from training, including their labels and model predictions. Then for each token, we'll find the nearest neighbors that minimize the Euclidean distance between representations. From these matches, we then construct a simple function to reproduce the sign of the token level prediction. Our KNN has 1 hyperparameter, K, and 3 parameters, beta, a bias offset, gamma, which is a weight against the available labels, and tau, which is a temperature weight for the relative distances. We learned the parameters with a BCE loss against the predictions from the decomposition. Looking at the results in the held out dev set with k equals 8, we see that the approximation matches the predictions reasonably closely, both with the zero-shot model and a supervised version. Importantly, the approximation yields predictions at least as strong as the original model when compared to the ground truth. Nonetheless, we might still be concerned that the accuracy isn't some smaller epsilon to the original model. And importantly, what exactly is happening in these cases when the approximation diverges from the original model? Let's think about these errors a bit more. So recall that I didn't actually say anything about the error term when I initially showed the functional form of the approximation. We're going to try to avoid modeling it directly to the extent possible. Luckily, there's a lot we can say about the errors in practice. First, when the KNN output does not match the original model output, those cases tend to be more likely to be wrong against the ground truth. And it turns out we can go well beyond that and further characterize the errors. This is informal terminology, and these two sources of uncertainty are related, but in broad strokes, we can think of the distance as the first match as a hard cut on the data domain, with input unlike that seen in training tending to have farther distances. And then the magnitude of the KNN output will be higher with more agreement across the support set. Now, in this paper, I don't show how to turn this into a particular coverage bound, which we show in a forthcoming paper, but instead focus on establishing that these signals are in fact in the directions I just mentioned in terms of point estimates. To analyze these signals and how they're useful in practice, we'll need a variation on our running task. We're going to add already correct news text to our student essay data. This data has a different distribution than the original training set, and in particular, the base models will struggle with false positives. So on this new set in the first row, we see that our f-scores nosedives. We've only added correct sentences, so we'd want the f-score to be similar to that on the original test set, which is in the upper 40s on this split for this model. But now we're in the upper 20s. Looking at the output, we get a lot of errant false positives on the domain shifted data. Now we can progressively winnow the set of predictions based on a cutoff of the k-NN output and or the distances. We see on this data and others that the distances and k-NN ensemble of predictions and labels are relatively strong signals as to the reliability of the predictions. Okay, so now we know how to screen input unlike what we saw in training. We haven't really gained anything in terms of robustness over such inputs, but at least we can detect when the model is more likely to go off the rails and treat such instances with caution. We can then get more data and retrain the full model, and in some cases that's our only recourse. But if at least the representations can match well against the new data, we may be able to just update the support set. In effect, we can view the support set as an updatable database. We can update the labels and new representations, add rationales, etc. To analyze this, we simply add some out-of-domain news data to the support set, disjoint from the support set, the test set, after which we see a dramatic reduction in the false positives, because although the underlying models are weak predictors over the data, the representations are able to consistently match the distribution. So, in summary, I've shown that we can transform a deep network into simple weighting over exemplar representations and associated labels, yielding an introspectable and modestly updatable version of the original model. Thanks.